Chapter 6, Number 7. The three identical boxes shown in the figure remain at rest on a rough horizontal surface, even though they are acted upon by two different forces, F1 vector and F2 vector. The rough part means that there is friction. That's the physics shorthand for there's some noticeable friction. All of the forces labeled F1 have the same magnitude, but of course different directions, and all of the forces labeled F2 are identical. Rank the boxes in order of increasing magnitude of the force of static friction between them and the surface. Indicate ties where appropriate. So there's a lot going on here, but in the end, what we're going to fall back on is that if we sort of draw a free body diagram, I'm going to draw a free body diagram for each of them. So there's our box, and of course there's some weight pulling down, and there's a normal pulling up, and then there's a static frictional force which will be resisting the motion, and then we have these sort of other forces to worry about, so which are F2 pointing over that way, and that so far really these are the same so far for all of them, so I'm going to replicate those and then modify them for F1. Alright, so those are all the forces that are the same in everything, at least not necessarily in size, but at least in directions and so on. But in case 1, we have F1, which points both downward, which we'll call like an F1y, and points to the right, which I'll call an F1x. But in case 2, it only points downward, so that's F1. And in case 3, it points downward, F1y, but also opposite, so F1x. So these are our three things. And then we're going to go and say, well, from Newton's second law, the sum of the forces in the x direction has to be whatever, but it has to equal m times a in the x direction, which is 0. That's actually also true in the y direction, but we're going to see that's not actually relevant. What matters here then is to say, since f of s is everything else, has to be opposite to everything else, we need to figure out how much rightward force there is, and fs would be the leftward force of that. So for box 3, we see that it's going to be, if we go down here, I'm going to say that for box 3, the horizontal force is going to be F2 minus F1x minus Fs has to equal 0. So Fs is F2 minus F1x minus some number. And over here, for box 2, we're just going to have that F2 minus Fs equals 0. So Fs has to be F2. And already we can see that that's greater than case 3, because case 3 is case 2 minus some number. I don't know what the number is, but it's minus that number, so it must be smaller than case 2. And then if we go sort of and finish with box 1, we have here that F2 plus F1x minus Fs equals 0. Just remember, let's keep these separated. And so therefore Fs is here, it's going to be F2 plus F1x. And we can see that that's going to be greater than case 2, because now it's case 2 plus some number. So our ranking is sort of the reverse of the order. 3 is the smallest frictional force, 2 is the middle one, and 1 is the least. Notice there's a lot of complicated things going on with F1y and Fn and Fg, and none of that's actually relevant to the size of the static frictional force because, and this is the important bit, they told us the boxes remain at rest. And since they remain at rest, we know the acceleration is 0. This would be, you could make a much more complicated problem and start saying, like, what are the accelerations in both cases? Or which one, as we increase F2, which one slides first? And things like that. We would need more details on the forces to answer those, and it would certainly be a lot uglier. But if we just want to know the size of the frictional force, this is it.